Hello, my name is Zach, and along with Zeping and Jeffrey, we are here today to talk about the Scalable K-means plus algorithm for our project in machine learning and optimization. We chose to do a pedagogical course project, so we'll teach you about the algorithm assuming no experience with the K-means family of algorithms. And actually, no experience with unsupervised learning at all. Everything we covered so far in this class will be enough of a prerequisite for understanding the following material. In addition to covering the topic, we will also demonstrate the results of a freshly designed empirical evaluation of the Scalable K-means plus algorithm. Scalable K-means plus is also referred to as K-means parallel, so you may hear those names used interchangeably as they are the same thing. We have also provided a problem set for the homework in the GitHub repository, which you'll have access to in order to help test your understanding of the material and further investigate new concepts outside of this presentation. In addition, this GitHub repository will have a notebook, data, and all the other code and information used for the empirical evaluations done in this presentation, so you'll be able to check that out. Lastly, you'll be able to find these slides on there. Alright, so this is a brief outline of what we'll discuss today. We'll first introduce the paper, which this project is based off of, titled Scalable K-means plus. Then we will proceed to go over what Scalable K-means plus is. It is important to go over the foundations first, however. We'll start with the K-means algorithm, followed by K-means plus, and then lastly, K-means parallel. It is important to mention that these aren't fully distinct algorithms. K-means is part of K-means plus, and also K-means provide the inspiration for K-means plus. Likewise, K-means plus is part of Scalable K-means plus, and K-means plus provided inspiration for Scalable K-means plus. The point is, in order to truly understand Scalable K-means plus, you need to understand the algorithms that came along before it. And when discussing these earlier algorithms, we will be indirectly explaining elements of Scalable K-means plus. So there is real motivation behind reviewing these algorithms first. We will first present these algorithms in a way which show how they came to be, meaning we will walk through what we imagine was the thought process of developing these algorithms in the order of creation, and discuss how each one improves on the previous. And as you'll see, the real difference lies in the initialization of these algorithms. Then we will go over an analysis of K-means, K-means plus, and K-means parallel, including the previously mentioned demonstration. And in the end, we'll summarize. So first, we'll formally introduce the paper. It is called Scalable K-means plus. The authors are Bahman Bahmani, Benjamin Mosley, Andrea Vatani, Ravi Kumar, and Sergey Vasilvitsky. It was published on Thursday, March 29, 2012, as Proceedings of the VLDB Endowment, and in their publication, they accomplished a way to drastically reduce in parallel the number of passes needed to obtain a good initialization for the K-means algorithm. And of course, we'll explain what all of this means soon. To begin, we will discuss K-means clustering. The K-means algorithm is a solution to a common problem in unsupervised learning. Now, unsupervised learning is a little different than what we have done during most of this course. With unsupervised learning, we are grouping data that we know nothing about, other than some pattern we have discovered. After grouping this data together, we will be able to apply supervised learning techniques, such as the ones discussed in class. Additionally, the grouping of data itself is useful in general. For example, when learning a new language as a child, you may be looking for patterns, or if you have a database of unlabeled movies, you may want to organize them somehow. Now, we describe K-means as a solution to a problem, and that problem is clustering. Clustering is a way of grouping data points. In order to group data points, there are things we need to figure out. The first thing we need to know is how many clusters we need. For the sake of this presentation and the algorithms, we will refer to this number as k. In the K-means algorithm, we make k clusters. The second thing we need to figure out is what makes a clustering algorithm good. For a clustering algorithm to be good, the points within a cluster should be close to each other, and at the same time, other clusters of points should be further away. And of course, efficiency is important. With each of these algorithms and the eventual scalable k-means plus plus algorithm, we will continue to improve the efficiency of clustering the data. The last thing we need to figure out is how we are going to cluster the data. Well, of course, we will be using the k-means algorithm, and in the following slides, the k-means plus plus and scalable k-means plus plus methods. However, the algorithm that we'll use for k-means clustering is called Lloyd's algorithm. We will describe the algorithm now, and it may be easier to understand with the example in the following slide. But first, in summary, we start by randomly selecting k points as centers. Again, k is the number of resulting clusters. This is the initialization step in k-means. Next, we go through each other point and calculate the distance between the point and the centers. Each point becomes part of the cluster, which center is the closest. Then we calculate the mean of each cluster and repeat the previous process, where the means of each cluster become the centers. And we reassign the other points to the closest cluster. We keep following this process until the clusters are no longer modified. It may be a good idea to repeat Lloyd's algorithm multiple times. This is because there can be more than one way to cluster the data, and the randomization at the beginning can result in different clusters. In the end, you can select the clusters with the least total variance. Now let's apply this algorithm visually. Our first example will be in one dimension for the purpose of simplicity. We will assume that k is equal to 3. Looking at these points, we probably have an idea of how we could cluster the data points into 3 groups. That being said, since the initialization is randomized, the results aren't necessarily what we have clustered here intuitively. Let's try it using Lloyd's algorithm. We begin by randomly selecting k centers, in this case 3. These are the centers. Now we look at the other points and cluster them to the closest center, as done here. After that, we assign new centers, and those new centers are the means of the previously resulting clusters. Now we reassign the data points to the closest centers. What we have just done counts as an iteration in Lloyd's algorithm. We keep repeating these iterations until no data points are reclustered in an iteration. If that happens, that means we are done. We call this convergence. In this case, since we did modify data points, we need to reiterate. Now we recalculate the medians of each cluster and make them the centers. This time, however, no data points were updated. As a result, according to Lloyd's algorithm, we are done. By randomly initializing the data the way we did and applying Lloyd's algorithm, we were able to successfully cluster using k-means. However, k-means is far from perfect, and there is certainly room for improvement. First, we can get poor clusterings of the data. Think of this. If the initial clusters are truly randomized, what happens if we start with 2 centers within some space that clearly should be the same cluster? As seen in previous examples, we can get different results, and many times we can get very poor results, especially with larger datasets. Larger datasets can also be a problem in another way. Specifically, they can take a really long time to converge with the k-means algorithm, and Lloyd's algorithm is NP-hard. We do not know when it will converge. Although it will eventually converge, it can be computationally difficult. But what if we did know how many iterations it took to converge? We can represent that variable as I iterations. In this case, assuming the dimensions are fixed, we get a runtime of ONKDI, where n is the number of vectors of dimension d, k is the number of clusters, and as said before, I is the number of iterations until convergence. Recognizing these problems, it leads us to wonder if there is a better way to cluster the data. Could we improve on k-means at all? What would a better algorithm accomplish?
An improvement on the k-means algorithm is k-means plus plus. K-means plus plus look to improve the runtimes of Lloyd's algorithm by picking smarter centers, thus making k-means plus plus an initialization algorithm for the k-means. So what does k-means plus plus do to improve runtimes? It picks centers based off distance from the dataset to all other centers, which ensures that centers are guaranteed to be far away from each other, which should lead to more accurate initialization. Of course, the question now is it actually better than Lloyd's algorithm with random initialization? And the answer is yes. As we have already discussed, the way K-means purpose picks centers makes the clustering more accurate, and the more accurate clusters lead to lower numbers of Lloyd's iteration to converge, which means faster runtimes. Something we want to keep in mind is that runtime is linear to or order of nkd, where data is the n times d matrix. So this is the official K-means purpose algorithm, which shows formally how each iteration is performed. First, we randomly select the first center from the data point at random. Then, for each data point, we compute its distance from the nearest and previously chosen center. Then we select the next center from the data point such that the probability of choosing a point as center is directly proportional to its distance from the nearest and previously chosen center, i.e. the point having maximum distance from the nearest center is most likely to be selected next as center. So we repeat the previous two steps, and once we have selected k centers, then k-means purpose has finished, and those centers can be used for Lloyd's iteration to cluster points together. Now, let me just clarify the algorithm by running through an example. And in this example, we'll try picking 4 centers from this very simple two-dimensional dataset. Here's what an optimal clustering looks like for this dataset, and each color represents a different cluster. So there are 4 different clusters here. So we pick the first center uniformly at random. So we pick this black point as the first center. Then we calculate the distance between dataset to this black point. And this green point has the furthest distance. So this point is most likely to be chosen. So we'll choose this point here as our second center. And we'll repeat the same process. Since this green point is furthest away from the both of the centers, so this green centers will be chosen as the third center. And same thing goes for the third center, the last centers. We'll choose this point as the last center, as it is the furthest away from all 3 previously chosen centers. And after we got the 4 centers, we give these centers to k-means, and k-means will calculate the clustering for the dataset. And this is the result after k-means. Yeah, so here is the final result of the k-means. So we explain what some of the benefits of k-means purpose are, but what are some of the problems? In k-means purpose, we pick one center at each iteration, which means we have to iterate k times, calculate the distance squared, and updating the probability distribution at each iteration, which is order of nkd, and is quite expensive. Not only is the runtime expensive, but k-means purpose is also sensitive to outliers, because the most likely point to be picked at each iteration is an outlier, because outliers are inherently far from the rest of the distribution, so we have 2 problems, runtimes and accuracy. How can we fix these problems?
So to fix these problems, we can use scalable k-means, or for shorthand, we'll use k-means parallel. K-means parallel was created by the guy on the screen, Bahman Bahmani, to improve the scalability of k-means++, and in his paper he showed there were 2 important factors to improving the scalability. The first one was the oversampling factor L. L is the number of points we pick at each iteration, so in k-means++ we just picked 1 point in each iteration and we did that k times, so we'd get k centers, but in k-means parallel we sample L points at each iteration in expectation. And The second important factor was that we only perform log psi iterations. So what psi is exactly is the time it takes to cluster the first point we pick. So the first step of k-means parallel is same as k-means plus plus, where you just pick one point uniformly at random. But the calculating of all the distances squared and the clustering together, that is what's stored into psi. And then we, instead of iterating k times over the data set, we iterate log psi times. And we actually, by reading the paper and doing some experiments, you see log psi is much, much less than k. And you end up with this this runtime of nd log psi, which is much faster than k-means plus plus. So now we can look at the algorithm, and the first step is same as k-means plus plus, pick the first center. Second is psi, that factor that determines the number of iterations. It seems like an odd restricting factor for determining number of iterations to do, but it has provable guarantees. And so then we iterate where C prime used to be k for k-means plus plus, so you just pick one center, and then you add it to your distribution with a probability of d squared. But this time we do probability of LD squared. So in expectation at each iteration we pick L points, and then we add these hopefully L points to C. And once we've done that log psi times, we get to step 7, where each point in C, we look at each point, see how many points is it closest to, as opposed to like any other point. So if you are closest to 2 other points closer than any other point is to those 2 closest points, you'll be weighted, twice as much as if you're just closest to 1 other point. And then in step 8, you recluster those weighted points and you get k centers. So you can do this using some other initialization algorithm, like k-means plus plus or Lloyd's algorithm. But once you've completed step 8 and you have your k clusters, then k-means parallel is finished, the initialization is done, and you can start running Lloyd iterations to find out which points actually belong to which clusters. So we're going to run through a familiar example of the data set for k-means parallel, just to clearly show the difference between k-means parallel and k-means plus plus. So we're going to look for 4 centers, have oversampling factor L equal to 3, and we're just going to start out doing the same thing as k-means plus plus, where we just pick one center uniformly at random. And the next step is to compute all the distances squared, cluster those points together to the first center, and store that in psi, so we have the proper restricting factor for the number of iterations we have to do. Next, we don't pick just one new center like k-means plus plus, but instead we pick L new centers, and we chose L to be 3 in this case. And then we pick the points in expectation with the probability, in the expectation that we pick L points with probability L d squared. So all these points you can see are about d squared, or they're the farthest d squared you're going to get away from the first center on the left. So seems about right. We then store those points in C, compute the distances squared to all other points, update the probability distribution, and then we're going to try getting some more centers. So next iteration, do the same thing, pick L more centers. You might think, we pick one center and then L more centers on top of that. We don't pick L plus 1 centers each iteration. That was just the first one because we had the first center and then added L to it. So it's just L centers in each iteration. And so we pick 3 more centers, and we keep picking L more centers until we've iterated log psi times. And let's just say, for simplicity's sake, that log psi is equal to 2, so we could just be done. And we now have the set C that has 7 centers, but we have k equals 4. So we have to move on to step 7, where we look at all these points and we reweight them based off of the number of closest points nearby, where the number of closest points you have nearby, say you have 2 points that are closest to you compared to all other points in the distribution, you would have double the weight of a point that only has one other point that's closest to it to any other point in the distribution. So we do this to gather which centers are the most important, have the tightest center on the data, and we recluster those to get k-centers in step 8. So step 8, you can use Lloyd's algorithm, k-means plus plus, but as long as you get those centers, you get 4 centers based off of the most highly weighted points, and you can end up with the same distribution as in k-means plus plus. So now I want to clearly state the differences between k-means plus plus and k-means parallel. So first difference is that k-means plus plus has to iterate over the data set k times, which takes a very long time, and k-means parallel only has to do log psi iterations, which I say here is less than or equal to n squared d squared, which really doesn't mean that much. But if you look at the size of log psi compared to k, in the paper, some of the experiments Bahmani was running, he would run log psi equal to 5 and k means plus plus, so that runs on k iterations with k equal to 500. So he was able to decrease the number of iterations by 100 times and actually improve accuracy, which, I mean, it's definitely interesting. So it kind of goes to show that k-means parallel is incredibly scalable. And this is due to the fact that k-means plus plus adds 1 center per iteration, and k-means parallel adds L centers per iteration. Another important thing about the L centers is that you want L to be around K or greater, and so this guarantees that you're sampling enough of your population. Like if you had L less than K, like significantly less than K, let's say L was 1/10 K, and you did 5 iterations, you're not even picking K centers, so you can't even get a representative sample. So it's good to be oversampling because you get more data than you need, and it can help provide more accurate results than undersampling. And the third difference is, like I've pretty much been saying, that k-means plus plus calculates k-centers, whereas k-means parallel calculates more than k-centers, significantly more, hopefully. And you generate L log psi centers in expectation, so that should be way greater than k. And I think it's important to note these runtime differences are pretty great, but can we expect accurate results with such a large difference in runtime? You'd think maybe we're not analyzing the data close enough if we're taking such a short amount of time. And surprisingly, yeah, we can actually expect accurate results from k-means parallel. Theorem 1 from the paper says if an alpha approximation algorithm is used in step 8, then algorithm k-means parallel obtains a solution that is an O of alpha approximation to k-means. So if we remember step 8, that's the step where we recluster the weighted points in C into k clusters. That's what this theorem is referring to. So theorem 1 is saying that if we use an algorithm with a known accuracy approximation, such as k-means plus plus, which has a O of log k approximation, then we can get the same accuracy as k-means plus plus, which is pretty nice. We just have to prove that it's a constant factor approximation. And he does this by showing that at each iteration, the cost of adding new centers to the set C reduces the cost of the solution by a constant factor plus 5 star, which is the cost of the total solution so far. And so he proves this using expectation of just adding the points to the set C, and it's a very convoluted proof, but that's the idea of it. He just tries to prove an expectation what the cost of adding points to the set C at each iteration is, and it gets this constant factor approximation of k-means plus plus. So now we can see the cost and runtimes differences with the experiments.
Now we will see how k-means perform with 3 different initialization. First, we'll look at a real-world image classification dataset, which is a letter recognition dataset with 16 dimensions. We need to cluster the alphabet letter image into 26 clusters. In the experiment, we merge the cluster cost, which is Euclidean distance of the dataset to their closest center. Cluster cost is like the cost function for k-means clustering. Out of 3 initialization, and we run each algorithm 15 times for consistency. K-means parallel has the lowest average cluster cost. Not only that, it also has the lowest cluster cost variance, as you can see over here. Then we look at the runtime. K-means parallel is at its best when it's run at parallel. Unfortunately, my computer does not have the best computing powers to show the true potential of K-means parallel, but we run the algorithm with 16-core CPU simulation that represent best CPU in the market, and the runtime is faster than the other 2 algorithms. The speed up is more significant as the dataset size increase, and when using a multi-core CPU, so CPU can optimize the runtime even further. Now we look at the experiment done on a synthetic Gaussian dataset with 16 clusters and 2 dimensions. K-means parallel on this dataset doesn't do as good as the real-world dataset. As you can see over here, the average cluster cost and cluster cost variance is still much better than the k-means with random initialization, and is on par with k-means plus performance. And more importantly, the runtime is still faster than k-means plus. As I said before, as the dataset become larger, the runtime improvement will become more significant. Now we look at this graph. In this graph, we show a trade-off between the runtime and performance. L over K is hyperparameter of the scalable k-means plus algorithm. L represents how many centers you sample at each iteration of scalable k-means plus. L over K equal to 3 means you sample 3 K points at each iteration, compared to sample 1 point from k-means plus algorithm. This will help you to eliminate some of the outliers, and outliers has lower chance to be picked as a new center now, which will give a better performance. But as a center, you need to sample at each iteration become more, the runtime will start to increase. So we need to choose L over K here, that balance between runtime and performance. As you can see, the green dashed line here, which has the highest L over K, yields the lowest clustering cost. And after initialization finished, the one with higher I over K also takes less iteration for k-means to finish. As you can see over here, the green dashed line takes 4 iteration of k-means, but the blue lines take 6 iteration, and blue line has less L over K. So in this presentation, we show an efficient parallel version k-means parallel of the inherently sequential k-means plus. The algorithm is simple and embarrassingly parallel, and hence admits easy realization in any parallel computational model. We also show that k-means parallel achieve a constant factor approximation to the optimal. Experimental result on real-world dataset demonstrate the power of k-means parallel. K-means clustering is the most popular clustering algorithm that usually the first thing practitioners apply when solving clustering cost tasks to get an idea of the structure of the dataset. Whether it's credit fraud detection, organizing featureless data, or any sort of data analysis, k-means parallel can be a useful way for processing the data for supervised learning. Thanks for listening to this presentation.